All right, we have talked about substitution, and we're going to keep doing substitution, but today's just going to add one more step because we're going to do a definite integral this time. So this time, instead of having our antiderivative and then putting our plus c on it, this time we have to plug in the top bound minus plug in the bottom bound and work through all that. Because notice we have some bounds now to work with. And we're going to start with one that you probably wouldn't need to do substitution to figure out, but we're going to do it with substitution anyway because it's going to help us see how definite integrals are going to happen. All right. What we're going to make u is the function that's inside of another function, which will be, right now we have the square root of y plus 1. Well, y plus 1 is inside the square root, so let's make that u. And then du, well, derivative of y plus 1 is just 1, so du equals dy. Integral. Instead of y plus 1, we have u, and instead of dy, we have du. All right. Here's the problem. If I wanted to plug in, well, if I'm looking forward and I'm looking at plugging in 3 minus plugging in 0, that's not going to work because I was supposed to plug in 3 and plug in 0 for y. But I don't have y anymore. What I have is u. And so instead of thinking about plugging in these numbers for y, we need to think about what would we need to plug in to u. So that means when we do a substitution, we also need to do that substitution for the bounds because we're plugging in to a different variable when we do our antiderivative. We're not plugging in for y anymore, we're plugging in for u. The good news is we won't have to do the step at the end where we substitute back in for u. The complicated stuff we're just going to deal with in terms of plugging in for u. But that means we need to figure out what to plug in for u. Luckily, this is pretty easy to figure out this time. U is y plus 1. And so we were plugging in 0 when we plugged in for y. So now for u, we're plugging in 0 plus 1 is 1. We were plugging in 3 for y, but now we're plugging in for u. So if I plugged in 3 for y, that would be 3 plus 1, which is 4. And you can double check. You can do this antiderivative and plug in the other way and see that what would end up happening, the thing that u, which is the thing underneath the square root, would end up being 1 for the bottom bound and 4 for the top bound. 0 plus 1 and 3 plus 1. All right, antiderivative. This is u to the 1/2, and so that'll end up being u to the 3/2, which means I need a 2/3 here to cancel it out from 1 to 4. So again, on the previous ones, we would substitute back in the y plus 1. Since I substituted the bounds, I don't need to do that. I'm just going to plug in 4 minus plug in 1. 2/3 times 4 to the 3/2 minus 2/3 times 1 to the 3/2. 4 to the 3/2, that is taking a square root and cubing it. So square root of 4 is 2, cubed is 8, minus 2/3. 1 to the 3/2 is 1. So 8 times 2 is 16/3 minus 2/3 is going to be 14 over 3. Is my answer. Good? All right. Next one. Oh, we got two different functions there. And so we need to figure out which one to make u. Either one will work, actually, but I'm going to work with making u tangent of x. The reason I'm going to make u tangent of x is my other big clue for what to make u is the derivative is somewhere else in the problem. Because what's the derivative of tangent? Oh, it's secant squared. And look, there's secant squared right after it. You can come talk to me. We can talk later on if you want to see how making u secant will work. But for now, let's make u tangent. Tangent of x. Du. That's convenient. What an amazing coincidence. Integral. Instead of tangent of x, we're going to put u. Instead of secant squared of x dx, that is just going to be du. Here's the bad news. We got to change the bounds. So instead of negative pi over 4 to 0, we need to change that so that we plug in our bounds here. So negative pi over 4 is our bottom bound, so we need the tangent of negative pi over 4. Negative pi over 4 is in the fourth quadrant, so it should be negative there. That's going to be negative 1. Tangent of 0 is 0. So the bad news is we had to do that evaluation and change in bounds. Good news, no more trig. The trig is gone from the problem. Because now all we have to do is say, oh, antiderivative, that's going to be 1/2 u squared from negative 1 to 0, which is going to equal 1/2 times 0 squared, negative 1 squared, which will be a positive 1/2. So we are subtracting 1/2. Taking 0 minus 1/2, that's going to be negative 1/2. Done. So in this case, just to recap again, we're not substituting back in like we were doing with the examples before, where we had to put it back in terms of the variable before we wrote it with the plus c. That's not what we're doing here. We are putting everything in terms of u and throwing out the tangent and the secant and all that to not worry about it and have to go back to it again when we plug in our bounds. But that does mean we need to not forget about switching our bounds when we do that. All right. We got one more to try, so go ahead and try the next one. On your own here. Don't forget to change your bounds. Since we already went through a square root 1, I won't show the whole thing of doing the antiderivative and plugging in, but I will show the u substitution part. Clue number 1. This was inside another function because it was in the square root. Clue number 2, the derivative was somewhere else in the problem. Derivative of this is 5t to the 4th plus 2 dt. What a coincidence. It's almost like they designed the problem that way. Like magic. Wrong! What do I need to do? Change your bounds. And you plug in for T and see what you get out for U. And 0's fine, but this needs to change. 1 to the 5th plus 2 times 1 is 1 plus 2, which is 3. So we are actually going from 0 to 3. Two root 3 should be the final answer, by the way, when you simplify it. All right.